Hi there, guys. This is 14Q, and this is the last section in Unit 14, and it's essentially about Bayes' theorem. So it's about switching around your conditional probabilities. This is a tough little final section for the chapter, to be honest. Right. So let's see what you're given here. So after the previous exercise, we go straight into an investigation, and it's essentially just the investigation which you have to go through in order to get the information for this. They never really tell you that this is Bayes' theorem or that what the formula is that you need to use. So what I'm going to do is I'm not going to do that this investigation, although if you look at the teacher notes at the start of the chapter, sort of the hidden icon for teacher notes, you will find the answers to the investigation there as well. What I'm going to do instead is I'm going to go through the first of these questions. So in the exercise to show you how that's done, and I'm going to give you a bit of theory on this as well. Now, if you have access to the old course textbooks, if you look at the old Cambridge book, I know I'm dealing with just the Oxford book each time here, which excellent as it is, the old Cambridge book does this quite nicely too. Right, so in that, if you look at exercise 22, it comes up with a really nice example to start off with on this. And this is where this idea of Bayes' theorem is often practical, okay, in the realm of medicine. Okay, well, I'll come to that in a second as well, because let's just tell you what it is to start off with. It's essentially turning around the conditional probabilities. So if you look at this thing here, we're saying, well, look, what's the probability of A given B? Well, that's your probability of, probability of A given B is the probability of A and B divided by, or intersection B rather, divided by the probability of B. But what's the probability of A and B? Well, you could write another one out. Probability of B given A is equal to the probability of A and B, or B and A, intersection rather, divided by the probability of A. So if you rearrange that, if you times by the probability of A there, you've got the fact that the probability of A is the probability of B given A times by the probability of A. Okay, so that's where we're getting this top part from here. So the idea of this is to switch around your conditional probabilities. Sometimes that's useful, sometimes that's the probability that you want to know. So if you know the probability of B given A, if you know the probability of A and the probability of B, you can find out the probability of A given B by using this formula. Okay, now actually it gets a little bit more complicated than that, in that normally the probability of B on the bottom comes from all of your options through a tree diagram. So what do we mean here? So if we say, let's follow the probability of, let's say the probability of A first. I hope it works this way around. Probability of B, and here we go. This is going to be your probability of B given A. Kind of done that a bit wrong, haven't I? Because the probabilities go on the branches, and the outcomes go on the at the end of the branch. So this is A and not A. So this would be the probability of A and the probability of not A there. If I put B there, I'm being crazy. Probability of not A. And then following that is B and not B. And this is now the probability of B given that A has happened beforehand. And this is the probability of not getting B, so B dash, given A has happened beforehand. And obviously you can come up with two roots down here as well for B and not B there. I just can't fit in the probabilities. Now, so if you're actually interested, you have all of these conditional probabilities on your second branches in tree diagrams. So if you have the probability of B given A, if you know what the probability of A is, you're going to need to know what the probability of B is in order to use this formula to switch around your conditional probabilities. Now, where is the probability of B? Well, the probability of B is this root and this root through your tree diagram. So often, this probability of B is now going to turn out to be, this is going to become probability of A times by the probability of B given A plus the probability of not A times by the probability of B given not A. Okay, so there's the two roots through the tree diagrams which you're going to need to add together to do this. Now, that's the extended formula for Bayes' theorem, and obviously it can get slightly more complicated if there aren't just two outcomes there. If you've got, say, for example, not just A and not A, but there's potentially three things there. Now, I'm not going to overcomplicate this anymore. Okay, and neither will the book, in fact. Okay, so but there is another slightly more complicated way of expressing this. Okay, so let's have a look at this example in the book from the old Cambridge book, in fact. So I'm not sure where this is going, changing color, but there you go. Right, so this one is saying, so a test for a rare medical disease is 99% accurate in the sense that the probability of getting a positive result, given that you have the disease, is 0.99. Okay, the probability of a positive result, given that you have the disease, okay, is 0.99. And that's the test for this rare disease. And the probability that you get a negative result, given that you don't have the disease, is 0.99. Okay, so there you go. So there's two probabilities there. Probability of a negative result, given that you don't have the disease, is 0.99. So it's 99% accurate in both senses there. It's 99% accurate for a positive result, and it's 99% accurate for a negative result. Okay. If you take the test and a positive result comes back, how likely is it that you have the disease? Now, that question is different to the 99%, because what we're asking there is not what's the probability of a positive result given that you have the disease. What we're asking is what's the probability that you have the disease given that you've got a positive result. Now, this is where the Bayes' theorem comes in, and that big tree diagram can come in as well, and we can switch around our conditional probabilities. Now, as they say here, the problem is that this probability you're interested in is probability of positive result given that you have the disease, but probability that you have the disease given the positive result is what you're looking for. These two probabilities can be very different. Okay. That's quite tricky to get your head around, I think. Okay, so they work through that in this case. You see that they've given you exactly the same formula I've found elsewhere as well. And they say often the hardest thing to calculate in Bayes' theorem turns out to be the denominator. So probability of B are many roots through a tree diagram. Okay, now there's tree diagram again. Okay, and your probability of getting A here, for example, is in fact the probability of getting B followed by A, so A intersection B. And the probability of getting A here, for example, is the probability of getting A followed by B dash. There's A intersection B dash. Okay, they've done it the other way around to what I did on my diagram, but fair enough. Okay, so there we go. So they've got an extended version of Bayes' theorem there as well with the different routes through the tree diagram. But here's the interesting bit. This is what I'm building up to here, is that it says, okay, well, if we apply Bayes' theorem in the disease detection example above, where the tests, remember, were 99% accurate, so that is to say that probability of A given B was 0.99, and here we're switching around to B given A. Okay, then and the probability of not A given not B is 0.99. Okay, implying that the probability of A given not B is 0.01. You kind of need to draw the tree diagram, to be honest. It says here, we do not have sufficient information to calculate this probability because the answer depends on the probability of B, which turns out to be the incidence of the disease in the population. Okay, so B is the probability that you have the disease, and A is the probability that there's a positive result. So there's this, the probability of having the disease is dependent on the incidence of the disease in the population, how common this is in the population. Now, if PB is very small, then so is the required probability. So, for example, if probability of B, in other words, 1% of the population has the disease, is 1 over 100 in this case, then when you put that into here, you're seeing that the required probability is 50%. So there's a 50% chance that you have the disease. However, if the incidence of this disease in the population is 1 in 10,000, then suddenly the probability that you have the disease based on your positive result goes down to underneath 1%. So there's this incredible variation there, depending on the underlying incidence of the disease in the population. Okay, so I mean, it says here we can make sense of this by arguing that the disease is so rare that a positive test is far more likely to be a faulty result, to be a faulty test rather than the result of a healthy person. Faulty test result of a healthy person, rather, sorry, than an accurate result of a diseased person. Okay, so that would be a nice IA project, in fact, that you could find some information about this, and there's a lot to discuss here, of course. Okay, but for you need to be able to switch around your conditional probabilities. So let's look at a question now from the book, and I'm going to skip the investigation there, but I'm going to look at this example here. So let's just take that down there. So we'll look at this example here, where we're talking about Bruno claiming he had extrasensory perception. Okay, this is a bit of a silly example, really, but I figured you'd want to know how to do the questions from the book. So it says Bruno claims that he has extrasensory perception. So a test is done in which 3 cards have one of 5 possible shapes drawn on them, and Bruno has to guess the shape on the cards. If he possesses some form of ESP, it is expected that he will have a better than average chance of guessing the cards. When the test is performed, Bruno guesses the shapes on all 3 cards correctly. Okay, so the test has happened. He's got them right. So that's done. Now, it says, explain why the p-value for the test is equal to 0.008. So there is, under the null hypothesis of no extrasensory perception, there is a 1/5 chance for each of these cards for getting them for guessing them correctly. And if you do 1/5 to the power of 3, that's the chance of being in the critical region, essentially. Okay, that's the p-value for this test. It's the probability that randomly, based on the null hypothesis, that he's got no ESP, then the chance of being in that critical region and of us making a type 1 error would be 0.2 to the power of 3, okay, which is 0.008. Then it says, and this is fairly tricky, this part B, it says, Bruno claims that this means that the probability he has ESP is the opposite of that. It's the 0.992, so 99.2%. Explain why he's wrong. Well, that's just the chance of him randomly not getting them right. Okay, what does it say in the answer? It says the probability is, quoting, is the probability of not getting all 3 cards right if guessing randomly. It's not the probability that he has ESP, because we don't know the prevalence of ESP in a population. I mean, we assume that it's 0, in fact, but maybe there's some evidence saying that it exists in a population. I mean, you can equally read that this is a disease instead of ESP. Okay. So it's really important to know what the prevalence of this of ESP is in the underlying in the population as a whole, because if it doesn't exist at all, then he doesn't have it. If there is no chance of having an ESP, then there's no chance he has it. That's just random. He randomly got them right, okay, which is what we expect, to be honest. Okay. So part C says, explain what else you would need to consider if you were to try and find the probability of the existence of ESP. Okay, well, they're not asking about whether or not he has ESP here. They're asking about the existence of ESP. If it's about him having ESP, then you think, well, we need to know about the prevalence of this in the population as a whole. But in terms of the probability of the existence of ESP, well, in terms of this test, you're going to need to make sure that it's a fair test, it's a reliable test, it's valid and reliable. It's reliable as in you can repeat it. It's valid in that there's no cheating possible there. So, there's no marked cards or anything like that. Okay, so in the next part, it says let H0 be the event that the results were obtained by chance, and H1 be the event that Bruno has ESP. Let D be the event of obtaining the result or a more extreme one. Okay, so D is he has ESP, or that's the conclusion. Okay, so then it says from other data, just a little bit further on this one, so let's just make this a little larger here. So then it says, and let's bin this, okay, let's get rid of that. So then it says, from other data, the researcher believes that the probability of ESP exists in 1% of the population. So draw a tree diagram. Unfortunately, they give us some advice as to how to draw the tree diagram here. So draw a tree diagram to show the 4 possibilities from the test, with the first 2 branches indicating having ESP. Okay, and having ESP, that's the decision from the test. Okay, having ESP and not having ESP. So having ESP and not having ESP, let's just hide that up a little bit. So that's according to the underlying population, and the null hypothesis is that 99% of people don't have it and that 1% of people do have it. So we're looking at the underlying population there. Now, we've obviously done this test with Bruno specifically, and we're testing now whether Bruno has it. It's a bit like when we've done tests before and saying, look, we've now taken a sample and we're seeing if this sample still reflects the original population. Okay, so draw the tree diagram. So we've drawn this. You may assume that if a person has ESP, they will guess all of 3 cards correctly. So following on from what happens in the population as a whole, which is what they've told us to put on the original branches, we've then got the result from this test, whether or not we think Bruno has it. So that is to say, are we in that critical region in the case of Bruno having it? I don't know if I've said that right. Are we in the critical region based on whether H0 or H1 is true? Okay, so the chance of him having it, if this exists in the population, if it doesn't exist in the population, the chance that we will decide that he has it is our type 1 error. Type 1 error is the 0.2 to the power of 3. And the chance, that's him randomly guessing 3 times, yeah? And the chance of him not having it is, or us concluding that he doesn't have it, in the case that 99% of the population doesn't have it, so following on from that, then if he ultimately doesn't have it, but then we conclude correctly that he doesn't have it, then that's the opposite of this. That's tree diagrams. You have to have these 2 branches adding up to 1. We have to go down one or the other. That's 100% of probability in total there. Okay. So then we also have the probability that we decide that he's got it, given that he does have it, that he is one of those 1% of the population. Well, if he has got ESP, they tell us that you may assume that if the person has ESP, he has ESP, then they will guess all 3 cards correctly. So that's 1 there. And that's 0 there, that he won't guess them correctly if he doesn't have them, if he doesn't, rather if he's got it and he guesses them incorrectly. That's not possible because he's got it. Now, again, that's a massive assumption. Potentially someone has ESP and in fact, they've got only some ability to get it right some of the time. Okay, but there you go. That's what they're asking us to do. Okay, we're done the tree diagram. Part E, extend, hence find the probability that Bruno would guess all 3 cards correctly. So all 3 cards correctly is basically asking us to then say, so, this is he's got it, this is he hasn't got it, but the chance of him guessing them correctly is this root and is this root here. So we're going to need to do our multiplications and add those together. So this times this and this times this, get 2 answers at the end and add them together in that case. So we're just looking for the chance of getting a D in the final answer. Okay, and that's giving us just under 2% there, 0.01792. Okay, and then it says Bruno has ESP. So that is the probability that he has ESP. Now, is that not this? Is that not what we assume from the start? Okay, Bruno has an ESP, but they're telling us that's the probability that he has ESP, given that, so that's the conclusion that H1 is true, given that, so the alternative hypothesis is true, that we conclude that he has ESP, given that D is true. D is true is that we have the result. So D is the result. H1 is that we conclude that he has ESP. It's confusing, this one. Okay, so anyway, they tell us what to do. They tell us what to do there. It's H1 given D. And H1 given D is not this, of course. It's switching our conditional probabilities around. Now, this is where the Bayes theorem comes in. And we can see it's pretty straightforward now. We've got the probability of H1, which we worked out, which we've got here anyway. That's this, times by the probability of D and H1. So that's essentially saying H1 and D. So H1 and D is this root here. So we just want the probability at the end of that, divided by the probability of D, which we've worked out previously. And now we can do that quite simply, and we get the answer of 56%. Okay, right. So then in part F, it says comment on which probability used was the least certain. Well, the least certain here wasn't the result from our experiment, I don't think. The least certain was this belief potentially at the start that 99% of the population don't have it and 1% of the population do have it. We really need to find the evidence for that. I would potentially say that this is also dubious, because we don't know that if someone has ESP that they definitely get things right every single time. Okay, so That to me is dubious as well. They've simply said the researchers believe that the probability of it existing is 0.01. Well, it depends on how rigorous the testing for that has been beforehand as well. Okay, and finally it says a different researcher believes that the probability of ESP existing is 1 in 1,000, not 1 in 100. And then that changes the calculation completely. And so we're getting the result of 11% there, which is drastically different to the 55%, 56%, which we got in the previous answer. It says, if this was the case, how would your answer change to part E part 2I? Well, it changes by going from 56% to 11%. There we go. I think the question is done. Okay, so this is tricky. We can see it's fairly tricky, but you're being led through these questions, and you could expect that this would be an extended question on one of your exams. You're being led through these ones. They're helping you in order to make up the tree diagram, and in fact, what you need to remember, of course, is that it goes back to this. It goes back to this Bayes theorem, which is not really mentioned a great deal in this at all. Let's get rid of me. It goes back to this thing here of saying that if we want to switch around our conditional probabilities, that's fine. We need to do the probability of A and B, which likewise can be written as the probability of B given A times by the probability of A, and then divided by the probability of B, which is your normal conditional probability. Probability of B comes from your tree diagram there. So what you need to remember is this, or the fact that the probability of A given B there's your normal conditional probability. You should be able to get it from there. Remember that you can change probability of A given B using the other version for conditional probability, and then your probability of B comes from several routes through your tree diagram. Okay, guys, well, I'm going to stop on that. That was pretty difficult to explain. What I would suggest that you do after this is actually have a look through the investigation. And if you're wondering where are the answers to the investigation here, then let's go back to the start of the chapter. So the start of the chapter was on page 570. So let's go 570 there. And if you go to the teacher notes, then in the teacher notes, let's open this one up. You can find, I think it was investigation 8. I've lost it now. So you should find it down. That's probably right at the bottom. So investigation 12, no, that's not what we want. Investigation 14, no, that's not what we want. It was investigation 8. But anyway, you can see that we've got here your various investigations. Well, I've lost it now, but they are all in the solutions here as well. Okay, so you should be able to find them in there. Okay, so thanks for listening in. That's the end of, oh, you know why? It's because I'm looking in chapter 13. That's why I'm being a doofus here. Let's go to that. It's pretty exciting, this video. So we wanted actually 622. Okay, so we go 622. You can open this one. Open this one up, and here we go. So it should be the last one. And there we go. So there's investigation 8. I would go through that. I would go through each of the questions from that. Okay, and you can see it works through those in the teacher notes there. Okay, right, thanks for listening in. Okay, just coming back to the wording of E part 2 here. It said, hence find the probability that Bruno has ESP. I think I was waffling a little bit on this one, and they say here, no, this is the probability of H1 given D. I think the probability that Bruno has ESP is H1, and H1 is 1%. But what they're really saying is, what's the probability that he has ESP, given that when Bruno tested, when the test is performed, Bruno guesses the shapes on all three cards correctly. So we're dealing with this extra knowledge. So we need to say, well, what's the probability that he has this ESP now that we know that that he's performed this test correctly? So this is a conditional probability, and I think potentially there's a poor wording there. It should now be saying, I guess it does say hence there, so it's hence following on from this information prior. Okay, so yeah, so instead of it being 0.1, which is the probability of him having ESP, but now we know he's done the test, it's now gone up to 56%. So given that he's done the test and got everything right, now we know that the probability of him having ESP has increased to nearly 60%, up from 1%. Yeah, okay, just to clarify that one. Okay, thank you.